All right, so this is the first of 2 weeks on statistics generally. Um, I know we have varying levels of statistical training in the class. Obviously, I can't teach you all of statistics, but I've found through the years that there's certain types of core concepts that are both applicable to journalism and sort of they don't come out clearly in a standard statistical education. So we're going to go through that, starting with the most neglected subject in statistics, which is measuring things. So that's what I mean by quantification. And then we're at the beginning of this, we're going to talk about things which maybe statisticians wouldn't talk about: quantification and data quality. And then we're going to go into risk ratios, which you've probably seen before. It's not a very complicated concept, but we're going to apply them to a story that the AP wrote alleging corruption, and really try to think very carefully about what's going on in this story. You'll see. It's every time I have this discussion, it comes out complicated. So that's good. And then we're going to talk a little bit about regression and causal analysis. And I'm going to try to show you how all of these things appear in journalism. And then next class, we're going to do statistical significance testing and a bunch of other fun stuff, randomization, bootstraps. How many of you have had like a 101 stats course? Yeah. So there will probably actually be very little overlap with what you were taught, because mostly, I don't know, I don't like the way statistics is taught. Quantification. So you saw this picture in the first class. The idea here is that we turn some complicated, difficult to describe, difficult to categorize reality into a series of vectors. So quantification is this arrow here, and a bunch of things happen at that arrow. A bunch of choices about what to record, and a bunch of lost information. And the lost information is normal. We call that abstraction. That is both what is powerful about quantification and what is weak about it, is we throw out things. So I want to talk a little bit about what we lose by quantification. And these are old critiques, right? I'm not going to say anything that people haven't said over the last 100 years. I just sort of want to talk about what this means in journalism. First of all, quantification can mean a bunch of stuff. We have, it's counting, but there's different types of scales. So you're all familiar with the difference between continuous and discrete scales at this point. There is structure. There are many different types of structure. For example, a continuous scale may or may not be uniform. So consider a Likert scale. You all know what a Likert scale is? So a Likert scale is a agree-disagree scale. Cigarettes are a healthy habit. Agree, disagree, 1 to 5, right? That sort of thing. Or maybe it's like a 1 to 5 star scale. How much did you like this movie? The thing about such scales is the difference between a 3 and a 4 may not be the same as the difference between a 4 and a 5. In fact, it's usually not, right? So think about rating your Uber driver. In theory, you could have 1 to 5, but in practice, there's a big difference between a 3 and a 4. So 3 and a 4 is a big jump, 4 and a 5 is a smaller jump. So the scales are monotonic, meaning that a higher number on the scale definitely means a higher number in reality in some sense, but they are not uniform or proportional. So you can't average them, for example, or it's not clear what averaging them means. Um, and then there are scales that are categorical and unordered. So, for example, if I ask someone to select their favorite color, it's hard to say whether blue is more or less than green. Like, what does that mean? And then there are scales that are categorical and ordered. Can anyone come up with an example of an ordered categorical scale?
Some and more.
Sure.
Not much, a lot.
Yeah, sure. Or, big, bigger, biggest. They're actually pretty common. So you can get things like ranks in the military or in a company. You can get things like the classification system we saw for classifying tweets as chit chat to news events. Discrete ordered scales show up actually a fair amount. More fundamental than that, I think, and certainly logically prior, are questions about what we're counting. So colloquially, we talk about the unemployment rate. Of course, there are actually many different unemployment rates. So here's a different measure of the unemployment rate, which is part-time for economic reasons, meaning that you wanted a full-time job, but you couldn't get one because you couldn't find a job, right? And so when we look at this unemployment rate, which is the standard unemployment rate, you can see that it falls slowly after the recession. If you look at this unemployment rate, which is I wanted to work full-time, but I couldn't, it doesn't fall nearly as fast. So depending on what you count, you literally get a different story. And this is part of what happens when people have very different frames on the same events, and we'll talk about that more. In fact, there are 6 standardly recorded unemployment rates called U1 through U6, and if you read them, you can see that they all give different numbers and they all count different things. So the one that is commonly reported is U3. It even says the official unemployment rate. So if you have to talk about the unemployment rate, that's normally what people are talking about. But there's lots of different ways to look at these numbers and tell different stories, because there's lots of different ways of counting. Does anybody know where these numbers actually come from? Like, how does the Bureau of Labor Statistics produce them? Surveys, yeah? Do you know any more about that?
No.
Okay. Has anybody looked into this? It does come out every month, yeah. So there's actually 2 surveys that are done monthly. Of course, there's samples, because you can't talk to everyone monthly. One of them is the household survey, and one of them is the business survey. And the household survey takes a survey of houses and asks, are you currently working? Have you been looking for a job? These types of questions. What industry do you work in? The business survey takes a sample of businesses and asks, how many people do you employ? Do you plan to lay people off? These types of things. And so actually, these 2 serve as an independent check on each other, because they don't collect all of the same data, but they collect enough crossover that you can check the accuracy of the surveys. So that happens every month, and I think there's about 100,000 people on the household survey. And the margin of error is large. When you're talking about estimating a fraction of 300 million people, 1 or 2% margin of error starts to be millions of people. So, for example, the job figures, you may have heard the job reports, the economy gains 200,000 jobs. The margin of error on that is plus or minus over 100,000. So that there's actually way less information in that than is usually reported. It's a crime that is reported so authoritatively. It's something I've been banging my head against for years, but nobody wants to hear it. We'll talk about noise a lot next class. We're going to talk about randomness.
Even the historical comparisons are always made with the same mark, like the survey that comes out. Like the survey doesn't improve or change. So like people take it.
The survey does change over time. So, I mean, slowly. Also, the unemployment numbers are revised after the fact. 6 months later, the government will say, "Oh, we're revising this up 0.2%." Yeah, and in fact, sophisticated economic models use two sets of numbers. The official, when you run them, when you backtest them, the official corrected numbers and the numbers that were available at the time, because you want it to work on the numbers that you have when you want to make the prediction.
How do they do the correction?
How do they do the corrections? I'm actually not sure why they correct it or what their rationale is. We'd have to look into particular cases. This is another way to look at the unemployment rate. We can sort of slice it by, here we go, number of states above a certain level. And what we get is this sort of contour map. There are a tremendous number of ways to tell the story about what unemployment, what happened to unemployment during the Great Recession.
Does each color also include like numbers from the color under it?
Yeah.
Oh, okay. Got it.
Yeah, it's think of it as a
Like
contour
states
map.
can be in numerous series, right? That's what
Yeah,
it's-
right. So if you're at 10, you're also at 9 and 8 and 7.
Okay.
Let's talk about GDP. You've all heard GDP. Do any of you know how it's counted? Yeah, like that.
Side of the back.
But think about it, right? So where do these numbers come from? How do you know what investment is? How do you know what import is?
Don't businesses have to like file paperwork and stuff for importing and
Yeah.
investing?
Yeah, so there's going to be official documents of various sorts. A lot of this comes from these surveys again as well. So it's got some error in it. To get consumption or equivalently production, that's done with a survey of businesses as well. So that's an intentionally non-random sample usually. It's stratified normally, which means it's weighted to include some big businesses, some small businesses, businesses in different industries. Stratification is a sampling technique which can give you a more accurate result for the same amount of work. We talk about GDP like it's this, as they say, naturalized concept, right? Growth. It's, everybody knows what economic growth is, but it's actually this very complicated thing. And here's another picture of it. It's defined to be to measure a particular set of flows. And I still meet economics reporters who don't really understand this. So I guess my lesson here is don't use numbers that you don't know where they came from, because otherwise you won't be able to see the stories, right? So if you say that GDP fell, even just looking at this as an equation, is that because there was less consumption, people were buying less, or because the government cut back spending on social programs, or because there were more imports, right? Those could all be different stories. So if you just write the headline story that says GDP fell by 0.3%, it's hard to say what that actually means.
Why is government's spending included in GDP?
Included in GDP? Because the government buys things. So if the government buys paper, then the factory produced that paper. And we're trying to measure total production, but because production is always consumed by someone, it's actually counted as consumption. You can actually calculate GDP a number of different ways, which are in theory equivalent, right? So in theory, everything that is produced is either consumed domestically or exported. So it's thinking of GDP as counting consumption instead of production, but actually they should be the same thing. Yeah.
So the calculation for GDP would be different for each country, or like
How they calculate it?
Yeah, or like statistical.
There's international accounting standards, and there's a bunch of problems related to the fact that different countries use different standards. So, for example, China switched its GDP accounting about 10 years ago to get closer to international standards, which means that you can't really compare GDP across that switch very much. Yeah. So I don't know if you've ever looked into accounting standards, but this entire field. There's big, thick books of what they call GAAP, GAAP, Generally Accepted Accounting Principles. This is a huge body of lore on counting. How do you count things? So my point is that you make choices here.
And who's doing the audits? Who's auditing?
Who's auditing GDP?
Yeah, well, like who's making sure that all these countries are adhering to those standards?
It's a really good question. Sounds like a story.
Not it.
There's definitely been scandals involving suspicious GDP numbers. Again, China stands out as an example. For many years, it was basically exactly 7%, or 6.8 or 7.1 or something. And I have a bunch of papers about how Chinese GDP figures were thought to be inaccurate in a variety of ways. Basically, political pressure on the local governments to report particular numbers. One of the indicators there is that Chinese GDP volatility is lower than any other country, which is interesting because it could mean that there is a problem reporting numbers. It could also just mean that China is really big, right? If you have lots and lots of people, that's going to tend to average out the noise. But the question of Chinese economic reporting accuracy is this whole subject.
Who oversees it?
What do you mean?
Who's the authority in all this?
Well, I mean, ultimately, they're the national governments, right? They have sovereignty. They're the one reporting the figures.
Exactly. So.
Okay, fun fact. The global accounts of the world do not add up. They're off by, depending on how you count, 5 to 10%. So that is to say, if you add up so every country reports imports and exports. If you add up all of the exports of Venezuela to France, as reported by exports from Venezuela, they are not equal to the imports from Venezuela to France as reported by France. Right?
It doesn't sum to zero, basically.
Yeah, exactly. It's according to global economic trade data. There's huge amounts of money that just disappear. And by the way, these amounts of money dwarf things like foreign aid. This is far larger than the amount of money that's spent on development aid. And a lot of this is financial crime. In fact, most of it is thought to be financial crime. Yeah.
So as someone in a nation within reporter who gets these numbers, is there like responsibilities just like assume fact and like take it up like externally, or we do something figured out like account for whatever?
I mean,
Misnomer or whatever.
all I'm really saying is that if you're going to use a number, you have to know where it comes from. And we'll develop a list of questions to try to understand this. A lot of reporters don't understand what their numbers mean. Okay, so some things are just very difficult to quantify. So one of the things that I've dug into the history to is the history of the quantification of race on the US Census. So this is what census enumerators were instructed to do in the 1940 U.S. Census. So this is a very complicated process, right? You're supposed to look at this person and apply all of these rules to decide what race to write down, right? So, yeah, right. There is literally the one drop rule right there. Should be returned as a Negro, no matter how small the percentage of Negro blood. And in fact, the form had quadroon and octoroon on it, meaning a white person with one black grandparent or great grandparent. So you were supposed to be able to figure out their ancestry 3 generations back by looking at them. Needless to say, this did not give very accurate counts. And in fact, after the 1940 census, there was some research that discovered that many minorities were being undercounted by millions because they weren't being correctly identified as non-whites. So they changed the way that the counting was done. So this is what it looked like on the last census. And how it works now is you ask the person what race they are. So now it's self-reported race. So what do you think? Is this an improvement?
Wait, so how did they do it here? The census person just decided, or what?
No.
Self-evaluation.
Yeah, this is. Yeah, you fill out this form on the census. Yeah.
In the 1940s, was there any reasoning behind why it was like you get like the person who's taking the survey gets to decide? Like, why was it?
Because that's just how they'd always done the census. So how the census is done or was done at that time, I mean, there are still enumerators, but not as many, is someone would go visit each person's house and ask questions and write down their answers, like fill out this form. And there were these complicated rules about how you're supposed to report race, and they switched in the can't remember if it was the 1950 or the 1960 census, to having people self-report race because people were being miscoded as white. It was particularly bad for the Native American population. It was, if the enumerators ran into someone in a city, that it wouldn't even occur to them that maybe this person has Native American heritage. So that was the goal, was accuracy. And in particular, the US uses a very weird categorization of race versus ethnicity. Hispanic is considered an ethnicity, not a race. And the reason for that, anybody know why, by the way? There is actually a reason. Afro-Cubans, Black Hispanics, that's why. When the system was designed in the 1970s, they needed some way to record that. And so they said, okay, well, we're just going to make race and ethnicity these separate things. And this leads to all kinds of problems. I actually wrote quite a lot about some of these issues in the Curious Journalist Guide to Data, so I'm going to give you a link to an entire chapter I wrote on race and a real-life story of a reporter getting into trouble trying to join 2 databases, and one database recorded Hispanic as a race, and one database reported Hispanic as an ethnicity. And so when he did a database join, here you go. He missed all of the Hispanic names until he figured out what was going on. So just because you think you know what a variable means doesn't mean that the data you have recorded it in the way that you interpret, right? So there's, you'll get a database which has a column that says arrays at the top. You have no idea what that is until you start digging into the production process for the data. You don't know how it's recorded. You don't know how they got that information. What the hell is that?
You mentioned before that the 1940s way of regarding race might be better in certain situations.
Mm-hmm.
I wasn't even understanding exactly what it would be.
So say you're trying to study some aspect of let's say the phenotypic portions of race, right? So what somebody looks like, as opposed to say how they behave, where they were raised, where they live, right? Race isn't appearance, but certainly people's appearance changes how they're treated. So one of these ways of recording race takes into account appearance more than the other. So it might give you a type of information that you want if you want to look at correlations between appearance and other variables. Right? So it really depends what you're after with the data. So it's often hard to say that there is a uniformly better way of quantifying any particular thing. There are ways that are better for particular purposes. So for the purposes of knowing how many Native Americans there are in the US, asking people, do you have Native American ancestry, is way better. But for other purposes, it might not be. For the purpose of knowing how many Native Americans there are who no one knows they're Native American, it's not going to be the data that you want. So we record a lot of things that are actually very difficult to quantify. So things like intelligence, for example. Oh man, the fights that people have had historically over the quantification of intelligence, and what does IQ mean, and are these tests biased in one way or another? And it's just every one of these things on this slide has this whole history of arguments about how to record it, and not just how to record it, but how to use it. And even something like income is way harder to quantify than you would expect. Does anybody know what some of the problems are just trying to quantify income?
Taxes? Cost of living.
Yeah, right. So taxes, cost of living. Do you include government services in their income? So if you're going to analyze income inequality, do you analyze the cash that they were paid, or do you analyze the cash they were paid plus all of the free services they used, right? Do you analyze healthcare that they received that their insurer paid for? Do you analyze the subsidies of the schools they go to and the roads they drive on, right? There's all of these questions about what counts as income. Nonetheless, we quantify these things and we can get useful information out of them if we work with them carefully and understand their limitations. So all of that was just on the question of how do we count something. Now I want to talk about the issue of, is the data any good, right? So not what are we counting, but is it counted the way it's supposed to be? So why do we have data quality problems? What problems do we end up with when we try to quantify things? Let's make a list. Not timely. So okay. Can I write out of date?
Data entry error.
Data entry error, the classic fat finger. Okay. What else?
As the thing that you mentioned, like people use the same word in to mean different things, so then you can combine data sets anymore?
Yeah, so let's say different definitions. And if the data you have was combined from multiple data sources in ways that were incompatible, you may not even know.
Participation and completeness.
Yeah. Completeness is a big problem. This is a problem that the polling industry has had to solve in a big way, because apparently 90% of people will hang up when you call them to do a survey. So then what do? Actually, anybody know the answer to that? How modern polling works?
Extrapolation.
What's that?
Extrapolate through complicated statistics.
Yeah, pretty much. So you combine different types of polling data. So you do things like, first of all, you weight the sample you do have for demographics. So, if you call people and you discover that, you only have 10% of your sample is 18 to 35, but you know that actually 18 to 35 is 30% of the people that you are surveying or trying to survey, then you can multiply that sample by 3. You can combine online polls and phone polls. Polling has become this incredibly complicated thing, and we'll talk about that more later. What other data quality problems do we have?
Selection bias.
Yeah. Tell us, what about selection bias?
So, like, the people who are home when you call are going to be a specific demographic of people.
Yeah.
Or the people who decide to answer your survey are going to be a certain kind of people.
Right. Right. Exactly. So,
Participation bias.
Or even the kinds of questions you curate could be like you may not even have field that you rate in when you create the survey. Just don't account for things that may apply to everybody. Like your bias plays into like the way you make the survey.
so the questions on the survey. Okay. Yeah. So let's call that survey design.
There's also a thing, again, related to surveys, but this came up in my internship, was that during a phone call or an in-person survey, people tend to overplay their good qualities and underplay their bad qualities, as opposed to like an online survey where you're more honest about
Yeah. Okay.
answering.
So let's just call this lies. That's a category of data quality. What about more technical problems? There's this whole category of just
Machine readability.
yeah. And in particular, there's a sort of accessibility bias. You're much more likely to use the machine readable records. You saw handwritten notes in the documents that I used for the Iraq story. I mostly didn't use that material because it was too annoying. Who knows what I missed? You've got the whole category of like data conversion issues, right? So, you've got, it's this long list. You start to get some things like, missing files and bad formatting. You've got, this is a very large category, inconsistent, what should we call this? Inconsistent values. So, is the US always spelled US, or do we get U.S. Or do we get United States, or do we get United States of America, or do we get USA, or do we get America, right? There's lots and lots of different ways of recording that, right? There's all kinds of issues. There is, I think, safe to say, no consensus on how people of Hispanic or Latin descent identify themselves now. You see that in census data. Some people write, let's look at this form again. So some people will write in Hispanic in that field, or Latina in that field, Some people will identify by their country. They'll say, I'm Mexican, or I'm Brazilian, or Guatemalan, or whatever it is. And if different databases or different people record this in different ways, and you try to aggregate them in some way, do you have all the categories? I don't know what to call that. Inconsistent identification, maybe? You get these cases where there's actually no agreement on what people want to call themselves. Then you get a bunch of just plain old errors, like truncated data, missing rows, and we haven't even gone into the economic or political reasons why someone would report count one thing and not another.
Wait, what do you mean?
What do I mean?
What would be an example?
I will show you. So you can have data quality problems that are not even intentional, that are just the result of technical errors. So that's that first case there. When the Los Angeles Times they built a crime map using a live data feed from the police department. And when they did that, they discovered that 40% of the crimes in the books were not coming through that data feed. And this apparently just turned out to be a technical error. It's like, well, nobody had really looked closely at that API, and it wasn't working. So they wrote this story about this problem. So by the way, that's always an approach to handling data quality problems. If you think you should be able to get data because it is public interest data and you can't, that's a story, right? You can always write the story about how we don't have access to this critical data. Maybe it's not as good a story about, here's our analysis of this data, but lots of examples where writing the story about being unable to get the information was an important story and resulted in the information becoming available. Or here's another issue, the second one. This was a New York Times story some time ago, and this is about different police officers having different conceptions of whether to record something as sexual harassment. So who you run into when you're reporting this crime affects whether it's reported as a crime. So think of any sort of data entry process, right? So for example, the serious assault cases that the LAPD underreported, somebody's going through and reading that description. Maybe it's the officer, maybe it's a data entry person, and checking a box, right? Is this a serious assault or not? Different people have different standards. Changing definitions. Oh my God, the fights that people get into over definitions. Just, we're seeing, this is a long-standing one, but we're seeing this right now. What counts as a rape, right? How do you know how many there are? I taught an entire workshop which was around use of data for gender advocacy, and that's one of the things we dove way into is what is the history of rape statistics and how do you record them and what definitions do you use and what methods do you use. And you get into things like the privacy of reporting. There's a standard crime victimization survey where somebody goes and visits someone there in the home and asks them if you've been the victim of a crime. And if you're asking someone about domestic violence and the partner is standing right there, you're not going to get a very good answer, right? And then what wording do you use to ask for? There's a lot of variation in the process that may have produced your data. So let's take a sneak peek here. Yes. So this is another example. This is from some work I did with Indian data journalism organizations, and one of them produced this beautiful example of being able to tell that the data was wrong just by looking at the data, right? So we've been talking about a lot of what I call external checks, where you go and talk to the person or try to figure out how the data was recorded. This is an internal check where you can just look at the data and see that there's a problem. So their claim is that traffic accidents are being underreported in these two cities. Now I've forgotten which state is Lucknow in. Thank you. Yeah. So they are finding problems with the accident statistics coming out of this state. And their argument is that the traffic accident deaths are about in line for the population, but the accident reports are way low. So what they think is happening here is that deaths are reported because they're kind of hard to hide. And this is a pattern we see in crime statistics generally. The more serious the crime, the more complete the statistics are going to be, because it's hard to hide serious crimes and people are more likely to report them. But the less serious crimes, I don't know what's going on. Somebody's not giving out tickets, or has a definition of accident which is very narrow, or who knows. But something's wrong with these numbers. As I was mentioning earlier, I sort of have this split in terms of methods to evaluate data between internal and external validity. And internal validity is just checks you can do on the data itself. For example, histograms can reveal a lot of important information about the data. You can see whether the data was quantized. You can often find format problems because you see a bunch of zeros. And often you know certain things, right? You should have exactly 50 rows for 50 states in this database, and if you don't, that's a problem. Certain numbers should add up. You might get derived figures like percentages. You can check all this stuff. But probably you're going to spend a lot more time on external validity, which is comparing to other data sources and comparing to people. And expert knowledge, which was the conversation we were just happening. Is this reasonable? Does this make sense? You see a lot of amateur data work where they just have no knowledge of the actual subject. And so they end up saying something just completely wrong. So the famous example of that is Null Island. Do any of you know what Null Island is? Or it's a city in Kansas as well.
Does it mess up everything?
This is a problem that happens with geocoding.
That's really funny.
Null Island is 0, so this is often what geocoding returns. The other thing is...
Yeah, I thought they were putting nulls in the tables and
It's like
throwing off all the
it's like the
interpreters.
SPC comic where they name their kid drop table.
Exactly. So if the geocoder can't find an address and just defaults you to the US, what you get is, I'm trying to find it. There you go. You get something which ends up exactly in let's see if this works. Oh. Anyway, you get this spot in Kansas, which is the geographic center of the United States. And so I've seen data analyses that have an oddly high number of whatever it is they're counting in Kansas, because that's where all of the geocoding errors ended up, right? So there's all of this crazy domain-specific stuff that you have to watch for. So in data journalism, we have this saying, interview the data, which means, treat it as a source and treat it with the thoroughness and skepticism that you would expect of a source interview. I actually have another page of these questions, but let's do this exercise. What sorts of questions, other than the ones on the board, should we be asking of our data?
Can we give like a specific context to the data? Maybe that would help.
Yeah, context. Context is a big word. Can mean a lot of things.
Oh, I meant for the purpose of the exercise. Can you give context into like what type of data we want?
Oh, any type of data.
That's yeah. Alright. Outside of that.
What else?
Were you supposed to ask any question?
I want to come up with a list of things to ask about the data before we use it.
What are the range of values for each given variable?
Sure.
Especially if it's especially if it's like a categorical thing and not like a numerative thing.
Right, like what values can it be?
Yeah.
Sure.
And like, what is the meaning of each column that you're providing?
Yeah. I mean, that's ultimately what we're trying to find out, but let's try to get a little more specific.
I think the example you just used like doesn't make sense just at first glance.
Yeah, the gut check. What about the politics of data production? How can we ask about people's motives in putting this together?
Where were they going to use it? Like, what was their intention of the data collection? I mean,
Yeah,
more
so we have that, yeah.
specific.
Who benefits based on certain values of the data?
Yes, that is an excellent question. Let's call it who benefits from certain answers, right? So there's a bunch of obvious things here, right? If you are reporting crimes, you want to see the crime rate go down, right? If you are reporting growth, you want to see the growth go up. And this is why we have accounting standards. It's because when people get to make up their own standards, they make up the standards that make their company look healthier than it is. Few of you haven't said much this class.
We should pick a random.
Okay, what else? There's let's come up with a few more of these.
Have there been like past surveys similar to this, and what are the outcomes of that?
Yep. Let's compare it. Yeah, absolutely. We should compare it to similar data, either historical data or other types of data that measure similar things.
Maybe just the basics, like what is the population sample that's being collected from?
Yeah, so let's call this the sample frame. What about definitions?
Ambiguous terms within it?
What's that?
Like ambiguous terms within the data, you mean?
No, like, we've run into all these cases where defining something is really hard, right? So what are you counting? Even things that seem sort of concrete have definitional problems. So say you're trying to count how many people have asthma. Well, what does it mean to have asthma? How do you count that? Right? And you can count the number of people who've been prescribed asthma medicine. You can count the number of people from medical records who have been diagnosed with asthma, but then that doesn't count people who moved in from somewhere else who have been previously diagnosed. You can count asthma emergency room visits. You can do statistical estimations based on these things. You can do population samples and ask people, but then how does their answer differ from the diagnosis? Like, even just counting the number of people with a concrete disease is an incredibly difficult thing to do. You have to make complicated choices about what you count. So I'm going to call this definitional problems. And then we have the problem of has that definition changed? So let's say history of data collection. If that definition changes in 2007, we went from counting prescriptions from asthma medicine to counting people who said they had asthma on a survey, we're not going to be able to compare before and after that date. At least not simply. So as usual, nothing is ever as simple as it seems. Here's some more from my list. We got a bunch of these in our discussion. The who benefits from this data is a really good question. Okay, so I think, any last questions on this? We're going to move on to the next section of the course. All right.
Just, I don't know if there's a specific question here, but I feel like a lot of this is related to data that's collected by like people or organizations, but like, are there, I guess, maybe similar or different issues that are associated with data that's like just automatically collected through?
Oh, sure. Right. So some data is collected by surveys or something. Some data is collected by logs of what people click on. There's all kinds of issues. Let's talk about that. What type of issues would you get with clickstream data? Lots. Okay. Bots. Yep. Yep. What else?
Magnitude, like it depends. Like let's say you're collecting number of clicks of people across the world. How are you going to possibly analyze that data?
Yeah, so you've got sort of technical challenges of the data size. You're probably going to have to make some approximations. Even counting the number of items in a database becomes a serious estimation problem when you start to get into the trillions.
Spoofing, I guess you deliberately lying, but
Yeah, right. And then I'm going to put downtime. Do we have complete logs? Did we lose the Kansas City data center for 3 hours yesterday? That sort of thing. Yeah. There's all kinds of problems even when data collection is automatic. Because it's not really automatic, right? It's a system that humans are creating and maintaining. As I like to say, software runs on people. And if you don't believe me, then why do you have to keep upgrading your WordPress install?
I guess we didn't talk about like someone not only lying about their data but trying to change other records.
Like falsifying records. Sure.
In both cases, right? Like, could be like even surveys or like automatic data collection.
I don't know where lies like I'm putting it back. Okay. All right, we're going to move on. We've got a lot more to cover today. Risk ratios. So this is a very simple statistical measure. And we're getting into this because, in part because it's an interesting thing that's used in a bunch of stories, and in part because it's going to prepare us for a deep dive into some machine bias stuff that we're going to do 2 classes from now. It's sort of going to be our introduction to confusion matrices. This was a story I was involved in when I was at ProPublica. This was one of the first times we got or anyone got access to a data set of police killings. And we did what may have been the simplest possible thing, which is compare the rates of teens shot by police for black versus white. In this case, teenage men. And so I made this little graphic to try to explain what was happening here. And I wanted to communicate a bunch of things. First, that the number was much higher for black teens than white teens, but also that these numbers were small in absolute terms. And so this is the diagram that I came up with. Now, for our purposes, the key thing that I want you to notice is this is not an analysis you can do with less than 4 numbers. You always have 4 numbers here. You've got the numerator and denominator for black versus white. But ultimately, we summarize them with one number, which we call the risk ratio. And that's what we're going to be talking about today. So it's in this case, it's 31 over 1.5. So what is that? That's 20 or so, right? And that was sort of the headline number in the story. Now, there's sort of a bunch of other difficulties in this story, including, the data set we got was this set of police records. It was very incomplete. Many departments don't report. But this was before people started building detailed databases. And so this was one of the first numerical estimates of the difference. Another example of this is a little more subtle. And in fact, this is a case where I think they should have used a risk ratio and didn't. So this was a story that came out in the summer of 2016 before the election. And one of the sort of narratives happening at the time was, let's look at Clinton's connections to the Clinton Foundation and whether there was influence there from her donors. And this was the top of the story that AP wrote. So take a second to read this, and then we're going to talk about it. Okay. So what's the narrative here? What are they saying?
Clinton abused her power as Secretary of State.
Could have.
Yeah, alluded to it.
Okay. So I want to work through the logic of this. First of all, do you find the story convincing? Does it seem to you like this is evidence that Clinton is doing political favors in exchange for donations to her campaign or foundation?
It's definitely a first read thing. A first read for sure. And I think you're surprised by those numbers.
Mm-hmm.
They're intriguing. But I'm not fully understanding what the claim is exactly. They're saying 85 people should only donate that much money. Okay, that's probably a fact. Of 154 people, who are these 154 people? Is that everyone she met? She only met 154 people outside of...
No, it's everyone outside of government who was on her calendar.
On her calendar. Okay.
Yeah, so that's what this is from. This is from a Freedom of Information request to see her calendar. So many public officials' calendars are available.
I guess it doesn't also tell me like what does her time in this, like it doesn't really correlate, like because she spent time with them they donated, like there's no clear way of saying that
you don't
this
even
is
know
a problem.
Or what they were asking for, or what she
Yeah.
did in return, like they donated, but
Did they donate
What was the
before
outcome?
or after?
Yeah.
Uh-huh.
I'd also like to see Obama's calendar when he was running for
Yeah,
re-election.
exactly. Comparison to like somebody else.
I'm sure he met a
who is-
ton of people that donated to him. It's not illegal.
Yeah, although,
Are all their meetings on their calendar? I mean,
right.
According to Brett Kavanaugh.
So right away we have got data quality problems, right? So what's measured and what's not measured. But I want to set those aside and focus in a little closer on this. This is the second simplest statistical model. The first simplest is to just count and count a proportion. Gives you with a single probability. So in this case, I'm looking, let's say there's a blue cab company and a yellow cab company, and I'm looking at the accident rate, right? So the yellow cabs have more accidents, but there's also more yellow cabs. So if we're asking a question about which sort of cab is more dangerous to get into, we have to take into account the relative, not absolute proportions, right? So we have to think of, the accident rate for yellow is this out of this. What about compared to this out of this? And given that there are more than 3 times as many dots here than here, whereas there's exactly 3 times as many accidents, this actually means that the yellow cabs are safer to get into even though the number of accidents was higher. So this sort of 2x2 table we'll be looking at a great deal through the next 2 lectures because it's a surprisingly subtle model. And the point I'm making is that to interpret this, we have to look at some sort of ratio. So let's see, here we go. I don't need to draw this, it's on this slide. So here's another common context. Instead of accidents and cabs, we now have smoker versus non-smoker compared to whether someone got, let's say, lung cancer. And the question we're trying to ask is, ultimately, does smoking lead to cancer? And to do that, I claim that we have to use all 4 numbers and we have to use them in this way. Does that make sense to everybody? So just working through the logic of this, we're looking at the fraction of people who had the disease who were smokers as compared to the number of smokers overall, which is A plus B, as compared to the fraction of people who had the disease who were non-smokers versus the number of non-smokers overall.
At a very minimum. Is at a very minimum how we can compare the 2, right?
I'm going to claim that this is the simplest possible way that you can compare these, you can look at this data. And that if you remove any one of these values, you can't answer the question you want to answer, which is smoking correlate? I mean, what you really want to know is smoking causal. Before you can get there, you have to ask for a correlation. And I'm saying you can't even see there's a correlation without using these 4 numbers in this way. Okay? Now let's apply this to the Clinton case. And let's think of a 2x2 matrix here. Let's see. So smoker versus non-smoker, I'm going to say that's donated, did not donate. Okay. And then what are the outcomes on this side? So what do I put up here? All right, what is the, if we look at this story, what are they saying the money gets you?
A conversation.
Yeah,
A meeting. Okay. So meeting, no meeting. Okay. So let's look at these numbers, try to fill this out. So that 85 and 154, where do they go?
85 goes to the donated in meeting.
Okay, 85 goes to donated and meeting. And the 154,
So 154 minus 85 goes to the
Did not donate but meeting.
okay, so what is that number? Anybody want to? 69? Okay, thank you. All right, so we have half of this table. So here it is. So, by the way, the way I've written it here is an odds ratio, not a risk ratio. A risk ratio is a ratio of probabilities. An odds ratio is a ratio of odds. Does everybody know the difference between odds and probability? Yes, no? Did we do this? No. Okay, so I will refer you again to my book and where it is, Accounting for Chance. No. Here we go. Okay. So here's probability. It's the number of, we usually say favorable outcomes, but it's just really the outcomes we want to count out of the total number, right? So if we ask what's the probability of purple, it's, well, how many purples out of how many of everything? Whereas odds are just favorable divided by unfavorable. So they're numerically related. You can calculate one for the other.
So in this case, probability would be one of the numbers by all four numbers. One by all.
Well, if you want to look at the probability, yeah, sort of, right? So if you want to look at the probability of they got a meeting, and donated out of the total number of people who got a meeting, it would be 85 out of 85 plus 69. So odds ratio functions very similarly to risk ratio. I said here that this is the simplest possible way that we can look at this. That's not quite true. We could just make this over B and this over D. So then we would have an odds ratio, not a risk ratio. But it functions very much in the same idea. And I've just done it this way to simplify it here. Right, so if we call these A, B, C, and D, the number that tells us whether paying is associated with an advantage in getting a meeting is what? Odds ratio equals I donated and got a meeting, so A over donated and did not get a meeting versus did not donate and got a meeting over did not donate and did not get a meeting. So what values of this would suggest that paying gets you a meeting? Right. So if this is greater than 1, then corruption? Question mark?
But this is not really.
Right. So this is not what this story is. What this story has is just this fraction, because we don't have all of these numbers. And in fact, if you're looking at a story which is claiming that paying money or giving some sort of favor gets you something back, then you should know immediately that you need 4 numbers, and if you only have 2, you don't have enough to conclude this. So this is a case where I'm still thinking about this 2 years later and sort of trying to wrap my head around the logic of this. But I think this is a case where there's less than it seems, right? We know that 85 people, all of those people met with her. We know that 85 were donors and 69 were not, but we don't know how many people donated and didn't get a meeting. So in particular, say this number is very large, right? Say she's got lots and lots of donors who don't get meetings. That means that paying for a meeting is not, or could mean, if this number is about the same, that paying for a meeting doesn't give you any particular advantage, because then A over B and C over D will be very close. Yes?
I just wanted to ask, it's very hard to estimate if you didn't give money and you had no meetings.
Yeah, isn't
Yeah,
that
they-
everyone else?
Yeah, exactly.
Yeah, you're never gonna get that number. Like, I didn't donate, I didn't get a meeting.
Well, okay, but these are of people who wanted one, presumably. And that's why I phrased it that way, right? So the question is, say you had tried to get on her calendar and you weren't a Clinton Foundation donor and you didn't get on her calendar, then you'd be in this box, right? So if these numbers are very high and about the same, then this goes to 1, right? So that's one way that these numbers might not indicate any advantage. On the other hand, say that that number is smallish, and this number is also 69. So that makes this 1 and that 8. That's very high, right? So if many of the people, if basically nobody who donated didn't get a meeting, then that supports this argument. But we don't know what case we're in. And you can make reasonable arguments that any of these things are true.
How about the number of meeting slots that she had? What if she only could host 154
Ooh,
meetings in a year, which is very reasonable for Secretary of State.
So what that is that's putting an extra constraint on this. That's saying that A plus C equals some number of meetings per year. That gets us closer. That helps with our inference. That sort of reduces 1 degree of freedom. That's a good observation. In fact, one of Clinton's responses through her office was that this is a crazy estimate because it doesn't count all of the government people I met with, for example. And I'm sure it doesn't count. It doesn't count all of the people she talked to who she didn't meet in the office, right? So there's lots and lots of problems with this story. But the reason I wanted to bring it up is because I wanted to sort of work through the translation from the words to the numbers, right? And so if the right phrasing for the verbal claim we are making is paying money to her foundation got you a meeting with Clinton, then I think that this ratio has to be greater than 1. I think there's no other reasonable translation. Which means, so if you believe that, and I'm very interested to hear what you all think about that, because I've been thinking about this for 2 years, and I'm still not certain this is correct. But if you believe that, then this story is a bad story. The reporters just didn't have anything. And I think if that is true, then they should have known better.
Do you know them?
I don't know them personally. I mean, I used to work at the AP.
You were there, right?
I was there, but not when they wrote this story. Yeah, and there's also several thousand reporters at the AP. So,
Yeah, I feel like it's worded very strongly without the necessary implications, or there's no evidence to support it saying that if she was elected, it could mean this. That was like the lead.
yeah. Well, I mean, I think it does show something. It shows that she has deep connections between her State Department work and her Clinton Foundation work, which when you start looking into the details, so here's where we start looking past the data into the rest of this story, right? So she's doing things like, the Clinton Foundation is international development, right? And the State Department is also involved in international development. So we can say there's definitely crossover between her government work and her foundation work. That much is clear. So I think you can make an argument that she's entangled, and maybe that's a problem. And maybe the story is defensible on that ground. But what actually happened here is that they walked the story back. Actually, let me get the record of this.
Was that on the front page too? Or was it buried?
Well, the AP is not doesn't have its own. All right, so here's I wrote a long analysis of this exact problem, because this is something that we really want to do. We would love to find corruption in data, but it's often very hard, because just looking at who donated to what and who got what is not going to answer the question of whether donating gives you an advantage, because for that we need 4 numbers, not 2 numbers. They walked this back. Oh, the shruggy. Oh yeah, and then what I want to talk about is we'll also do a little bit later today is the causal structure here. Let's criticize. Okay, here we go. They changed the headline and deleted the tweet. So there's sort of layers and layers to this question. One of the problems is that I think they kept the story, but they changed the headline and the tweet. So that's an issue, is where the headlines don't match the content of the story. I think it is very interesting that she's so entangled between the foundation and her political life, but it's not immediately obvious what it means. And then ultimately what you would really like to do is be able to show cause. And showing cause is very hard for a variety of reasons. You have to show that this ratio is greater than 1, so you have to show that there's advantage. And you have to show that the reason the ratio is greater than 1 is that paying money gets you the meeting. And that gets into the issue of correlation, and we're going to talk about that shortly. How many of you have done linear regression before? Yeah, it should be all of you. Is that a no or a yes? Or you've never seen it ever? A little, okay. Yeah, I think all of you have at least seen linear regression. I want to talk about it briefly because I want to talk about how it's used in journalism. And this is also an introduction to the problem of causality, which we touched on briefly a moment ago. And very often, first we do a regression and then we try to make a causal claim. Yeah, okay, so here's one of my favorite multivariable regressions in journalism. This is old data. This is actually data from 2001. But the reason it's from 2001 is because for a few glorious months, we had data on both tickets and warnings for all traffic stops in Massachusetts. And at the time, the difference between a ticket and a warning was whether someone checked ticket on the form. So the police officer would stop you. They would do the do you know how fast you were going thing, or whatever their conversation they had. And then they decide to give you a ticket or a warning. And so it was kind of a natural experiment because we could look at the relative fraction of tickets versus warnings and see who got punished more. So a ticket is a fine, it goes on your driver's license, blah, 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 or your driving record, can change your insurance rates. A warning is nothing, basically. And so just by doing simple counts, you can get charts like this. Right, so, you get, men get more tickets than women, minority drivers get more tickets than white drivers, state police give more tickets than local police, and so on. The analytical issue here, of course, is that you don't know whether the drivers are the same in all other respects. So the data is actually very rich, and I'll show you the data very briefly. I have it loaded into a Workbench tutorial here. Where is this? We were doing this in the tutorial section. Tickets versus warnings. Here we go. So this, by the way, is, some of you have seen Workbench, some of you have not. Workbench is a code-free data journalism system designed for transparent and reproducible work. And so what you can do is you can publish this document, this workflow, along with the story. But here's what the data looks like. It's got all of this interesting stuff. So type, ticket versus warning. We know the day of week. We know which police agency gave them the ticket. We have the badge number of the officer. We have the race here just coded in a, you can see it's like, unknown, black, white, and it's got Asian, a few other races. You can see them here broken out. The sex of the driver, whether the vehicle was searched, where they were, what time it was, what type of citation it is. So the first thing the Boston Globe analysis does is just filter it out for speeding. So if I look at this filter here, that's what I'm doing here is I'm filtering out only for speeding and only things where I know how fast they were going. This is how fast they were supposed to be going. So we have a lot of information here. And if we take a basic analysis, this is that chart you just saw, which is the ticket versus warning rate for whites versus minorities. And then we can make that a little simpler by looking at those as rates of tickets. And here we see this disparity. It's on the next cell, what I actually do is I use a formula to calculate the difference. And it's about 19% different, 19% higher. Yeah.
Do you know who was putting down what the race of the driver was?
The cop was.
I assume. So it's like a 1940 census problem.
Yeah, so you have to ask about the accuracy of that column, sure.
And since we have the places, the person's badge number, can we get details of the officer who, like, can we do a profile of the officers who put out these tickets?
As a matter of fact, we can, and they did that. Here, I'll show you this package.
Is that the actual story?
Yeah, this is the actual story. It's an archive of it, but somewhere in here, there we go. Minority officers are the toughest. There you go. There's the graphic that they did about this. And let me give you the URL to the story. And you can download the original data as well. So this is a great way to play with multivariable regression. So anyway, these are just raw counts, but now you have to ask questions like, well, okay, were drivers of different age, race, location going the same speed, right? Or maybe, more minority drivers are from out of town, and out of town people get ticketed more. You have to account for all these other factors. So this is why we do multivariable regression, right? We want to try to account for all of these factors simultaneously. And you start to get words, you've probably heard these words, controlling for the speed that the drivers were going, controlling for driver age. You still got a higher rate of tickets. And the idea here is we take this statistical model and we try to reverse engineer it to compare people who are otherwise different. So if we find out that going 10 miles an hour over the speed limit versus 20 miles reduces your chances of getting a ticket by 5%, then we take all of the people who were going 10 miles an hour and we increase the rate by 5% and we see if that compares evenly. So this is classic multivariable regression, and it's introducing the idea of controlling for things. This was one of the stories that they give. I actually found this one was kind of fascinating because this was one of the only stories I've seen which looks for a disparity, doesn't find one, and then reports that. So we all know that's a problem in science with negative results being unreported. It's a big problem in journalism as well, and they did all this work. That, I'm of the opinion that you should just write a story that says, it looks okay. Because that becomes archival or reference. It becomes a reference point in these discussions. But you don't really see that. And I feel this is one of the places where a statistician or a scientist and a journalist are going to have very different ideas about what should be written. Another thing I want to point out here is that they actually didn't find that everything was identical. They found that there was a 2% difference. For the men, I guess. And they have this curious phrase. It says, these small differences are not statistically significant. We will talk about statistical significance in some detail in the next class. But, you know, when you compare big aggregate numbers like this, they're never going to be exactly the same. So then the question is, well, how much of a difference is important? Is a 19% difference important? Is a 2% difference important? If you're going to compare, you know, graduation rates or rates of, you know, men and women in management positions or any of these sort of diversity issues, there's no, I don't know of an obvious way to say that this is the threshold where the difference matters, and below that we don't care, and above that we do care. Even this statistical significance type argument here, they're using probably like a p smaller than 0.05 type of test. That's an arbitrary threshold as well. It's a complicated problem to try to turn a number into a binary yes-no. Oh yeah, that's what we were just looking at. This is another story which involves regression, but expands the frame a little bit to try to look at the overall question of controlling for multiple factors. So here's the original story. This is a recent New York Times story, and I find this a fascinating story for a number of reasons. One of which is that it's a story about a company making an audacious claim that seems to be true. They're saying that you can wear these shoes and run faster by about 4%. And, okay, but, ooh, it's interactive. Look at that. Ooh. Okay, so the naive way to do this is just to, so they had all of this information from this running site. They got it from, there you go, Strava. So they were able to get, you know, thousands and thousands of races. And the simplest way to do this comparison is just look at all the races where they were wearing these shoes versus not. That is a bad idea. Why is it a bad idea?
Well, over time, I imagine over a long period of time, that they were making these comparisons for different races. Same people, but different races wearing different shoes? Or were they just comparing people wearing certain shoes to other people wearing the Strava shoes or whatever their shoes?
Well, what they're actually doing is more sophisticated. So what I'm saying is, what if you did the analysis by just downloading all of this data and comparing the people wearing shoes to the people not wearing those shoes?
Well, maybe the faster people win races, get more money, and hence can afford the shoes.
Right.
Or sponsored.
Or run at night or instead of the morning. Apparently people run slightly faster at the end of the day. Or they could be running on different tracks. Or they could be just fitter athletes who, you know, like these shoes because Nike is marketing to particularly athletic. There's so many things it could be. So you have to control for all of this other stuff. And the Time story is different because they controlled actually in 3 different ways. You know, before the New York Times writes a story saying this shoe will make you run faster, like that's a big endorsement. They want to really nail this down. So so this top one, this statistical model, that is a multilinear regression. Okay, so you can think of this as finding the slope of the best fit line that accounts for all these factors, and then trying to equalize everyone else by subtracting off those factors. So it says, okay, we know people run faster at night, so let's take everybody who ran at night, subtract off the 3% advantage that gives. Okay, we know people who are younger run faster. So let's subtract off the advantage that gives and try to balance everything out and see if there's still a difference with these shoes. But that's not, and that's the classic method, but that's not the only way of controlling for factors. So they have these two other ways, right? When we compare changes in race times among groups of runners who ran the same pair of racers. So let's figure out what that actually means here. Where is it? Who ran the same pairs of races.
So the same pairs of races wearing either the Vaporfly or another pair of shoes.
Yeah, the third one is the same
Yeah.
runner once he switches shoes.
Yeah, somewhere in this article they have a little more description of exactly what they're doing. But that's the idea, is you take a person who ran the same race with and without the shoes, and then you take a whole bunch of these people who ran with and without the shoes and you look at the difference. And the idea is everything else is the same. It's the same person, it's the same pair of races. You hope, I guess, in this case that they're not always running the second one at a different time of day or something. But this is a different way to control for this effect, is they're choosing the data to hold everything else still. So rather than trying to build a model of the data, they're just picking people who are directly comparable. The same person running on two different races, or running hopefully on the same track, right? And then this is a different thing, which is you look at before and after switching shoes. So again, you kind of have to hope there's no correlation. They didn't do something else. They didn't do their total makeover program. I'm going to start training more and switch shoes. So that's a way you can still make mistakes here. But what they find is no matter how they run the numbers, these Vaporflies are still an outlier. So this is an example of a robust result. It means even when you change the model a bunch of different ways, you get the same answer. This is what we're looking for in data analysis. We're going to talk about this a lot more next class, this idea of robustness. And of course, you want non-data sources to also match. This is a big regression that I was involved in. This is Surgeon Scorecard. It's based on 5 years of Medicare data. It was the first analysis of surgical outcomes to name doctors. To do that, we had to account for a number of factors, including the characteristics of the patients, because certain patients would be more complicated or sicker than others, and the hospital that they're working in, because there's a long line of research that suggests that there is, in statistically, what we would call a hospital effect. Certain hospitals just have a higher quality of care. We also had to make the patient population incredibly uniform. So we did elective surgery only. So knee replacements, spinal fusions, stuff like this. Things that was non-emergency because they were much more simpler and uniform. And we screened out patients with a variety of pre-existing conditions and really tried to narrow it down. There is a long methodology paper that explains this. This was an extremely controversial piece. But one of the ways we tried to make it less controversial is by, rather than just reporting the raw rate, we reported the result of a model. And this is what that model looks like, and I'll try to explain this for you. So this solid line in the middle is every doctor in our sample, and we had, I forget how many, 10,000 or something, ordered by the modeled rate. And the modeled rate is what we reported. And so you can see that goes from about 1% to, it actually goes up to like 20%, but really it's like 1 to 5 or something. And then these dots are the raw rates for that doctor, meaning what is the actual number of complications out of the number of procedures they performed. And we had to define complication very carefully. In this case, we defined it in a way which is pretty common in medical work, which is readmission within 30 days for a related problem, which we looked at the diagnosis codes for the readmissions, because what we had were admission records. It's not a perfect way, but it's not an awful way either to look for complications. And the reason you get these sort of bands here is because these are often small number ratios, so this will be, if it's 6%, it could be, 3 out of 50 or something, right? And so what you're seeing are sort of whole numbers here. What you'll notice immediately is that the raw rates, as opposed to the adjusted rates, so ACI or adjusted complication rates, have a much wider range. And we also adjust for patient characteristics, like do they have a history of heart disease and so forth. But the unadjusted model, which is the open circles, you can see the open circles and the asterisks are almost on top of each other. There was very little change by adjusting for patient characteristics. So what's going on here is something called shrinkage. Have any of you heard this statistical term? The idea is this. We're trying to report a complication rate, but there's an element of chance here in what patients they get and what happens on that day in surgery and whether the patient gets exposed to an infection. So we don't expect that the raw rates are going to be accurate, right? There's chance in there. In particular, we expect that most of the doctors who have something that looks like a particularly high rate just got unlucky, and most of the doctors who had what looks like a particularly low rate got lucky. And so if you work out the optimal estimator for you imagine there's some underlying complication rate that is due to the doctor's skill or practice. And what we see is the outcome of luck plus or minus that rate. So if you try to work through the math and try to estimate that underlying rate as well as possible, what you're going to find is it's going to be narrower than the observed rate, which is what we see here. Right? What this model is telling us is it's saying that, we think that most doctors are actually somewhere around this average rate of 2.2%. And when we see something that's higher than that, we tend to shrink it down towards that average, either make it smaller if it's a very high number or make it bigger if it's a very low number. And this is a statistical effect you're going to see in lots of different analysis. So in this case, the modeling, rather than controlling for all of these other patient factors, was just trying to get a more accurate estimate by pushing everything a little closer to the average. Have you ever seen shrinkage before? So this is probably the most sophisticated statistical analysis that I've seen in journalism. I had the good fortune to be involved in programming some of this. And here, let me get the link for you. So they wrote this long methodology paper, which, man, if you want a crash course in statistics-based reporting, this is really something. And it's a gigantic logistic regression, ultimately. Now, this story had a lot of impact. It really split the medical community. Half of people were like, who is this news organization using this non-peer-reviewed methodology to critique doctors? Sort of how dare they? And half of the medical establishment was like, We've been trying for 20 years to get greater transparency around outcomes because preventable medical error is one of the leading causes of death in the US. Somewhere around between 200,000 and 400,000 deaths a year from preventable errors. And patient safety advocates have been saying for decades that one of the things that might help most is transparency around complication rates. Because you're referred to a surgeon, how do you know if they're any good? Now, it's not quite that simple. There's a lot of problems with transparency and complication rates. For example, they have to be adjusted for patient mix, which of course we tried to do to the best of our ability. And, the loop has to close. Just reporting that a doctor has a higher complication rate doesn't mean that complication rate is going to go down necessarily. It depends why and how patients and doctors and staff and funders perceived these rates. So it's not obvious to me that publishing this story will ultimately result in better medicine. What is clear is that it advanced the conversation that had been stalled for decades. And so now part of the critique process is other people are coming up with what they think are better measures. So it's really forced that field to move forward. Yeah.
I was just curious, like the data for this story was obtained from medical records, you said?
From Medicare. So that's government subsidized healthcare for older people, which is about 40% of the medical care done in the US.
So is there like a fire or like is it publicly available?
It was, so how this happened is the Wall Street Journal wanted to investigate Medicare fraud. So they actually fought a court case to get access to the records and did some stories about Medicare fraud. And then ProPublica was like, well, now that news organizations can get this data, what can we do with it? And so settled on this. And there was actually a complicated data use agreement between the government and ProPublica that they had to negotiate for and sign before they got the data. And the data use agreement included terms on privacy protection. So for example, see where it says redacted here, raw complication rate? Complications 1 to 10. If they were less than 10 complications, we couldn't report the exact number, because if you knew the exact number, like say you knew there were only 3 complications in a particular hospital, you might be able to figure out who they are.
Is that tied back like HIPAA?
Yeah, I mean, probably ultimately HIPAA, but also even if there was no HIPAA, you'd have general privacy concerns. You want to name the doctors, not the patients. So a complicated data negotiation, a complicated statistical analysis, which was basically a big regression. We did control for all of these patient factors, just like here we're controlling for different, who's racing and when and so forth. And here we're controlling for all of these driver characteristics. But here, mostly what we're getting is shrinkage. So the modeling is pulling everybody towards the average to try to balance out the effects of chance. Okay, so that's a few examples of multilinear regression in practice. Normally, why you do a regression, you look at the coefficients or you compute these risk ratios, is you want to assign cause. So let's talk about causal models. It's the last major topic today. Here is a graph of the Nobel Prizes per population versus chocolate consumption per capita. So clearly, Nobel Prizes, or eating chocolate, makes you win Nobel Prizes, right? Exactly. Here is some data from an old study on mortality versus smoking. So they knew the smoking rate and the mortality rate in different professions. When you graph them, you get this. So clearly, smoking causes people to die, right? Okay. So you all believe one and not the other. Why? There is some thing about cause that is not in the data. That's what I'm trying to demonstrate here, right? This has exactly the same logical structure as that, and yet you believe this one and not the other one. So what's the difference?
we can think of other variables that may be highly correlated towards chocolate consumption and Nobel Prize winning.
Yeah, so we can have confounding variables for sure. That's where this is going.
Yes, we have like more established fact that smoking is bad for you, which like makes you think that this should be more bad.
Yeah, exactly. So the difference is due to a story we have about how the cause works. In particular, we have, for the smoking case, we have in our heads a very good idea of a causal mechanism. So cause is not something that can really be inferred from the data. You can get evidence towards causation in the data, but by itself, the data can very rarely tell you there's cause, at least absent an experiment. And we'll get to what an experiment is in a minute. Here's another one, unemployment rate versus investment. So is this saying that if you invest more, you'll have lower unemployment? Or is it saying that when there's lower unemployment, you're going to see higher investment? Neither? Both? What's going on here?
Well, usually the x-axis is the independent.
Indeed. Normally the x-axis is the independent variable, and for that reason, it's easiest to read it in that direction. But actually, there's this paper that just came out suggesting that, really what we should do is turn all the charts sideways to prevent that, to prevent people from interpreting it that way. Now, I don't know if that will actually work, but it's an interesting observation. Not only do we always use the x-axis as the independent variable, but we very naturally talk about cause. And it's hard to even describe this graph without implying cause, right? So if I say unemployment rate goes down when investment to GDP ratio goes up, that sounds like I'm talking about a cause. I have to really work around it linguistically. I have to say something like, when we see higher investment to GDP ratio, we also see lower unemployment rate. It's actually, we're so wired to look for causes. And this can mislead us and our readers. So here's another one. This was also a story I worked on. There was a guy who, a few years ago, he was a professor somewhere who was looking at these figures and saying, well, the way to reduce domestic violence is to make sure women marry. Which, if you look at this graph, it's consistent with that story, right? Because, women who aren't married, which is the black and the blue here, have higher rates. Now, of course, one of the things that's happening when you dig into this data is that this is the crime victimization survey, where you sit there and you go to someone's house and you ask the woman in front of her husband, are you a victim of domestic violence? So not a very good survey for that. Might work okay for, have you ever been robbed at gunpoint, but not for this. And another thing that's going on is there's all kinds of potential confounders. So, for example, women who are more economically secure are more likely to get married. And if they're more economically secure, they're also probably more physically safe. So I wrote a story sort of beating up on that. This is from a site called Spurious Correlations. You can clearly see that eating cheese makes you more likely to die by being tangled in your bed sheets.
They brought this up at a conference recently.
Mm-hmm. And here's some more, as they say, spurious correlations. So, if we stopped funding the National Science Foundation, the temperature would stop going up. Right, and this seems very silly, right? But this is not a different case than this. right? We're also looking at a correlation here. It's just a question about whether we have a story that comes to mind, which is why the story is not good enough, why we actually need to break down cause in a more sophisticated way. So here's the beginning of doing that. I'm going to introduce you to a modeling formalism called causal graphs. And there is actually a mathematical interpretation of this stuff. You're looking at variables, and the arrow means basically that the distribution of y depends on the distribution of x. It says that they're not independent. And it says something more than that. It says that if you change x, y will change. And this is the idea of cause. You can't capture causes in correlations. You've heard that many times, but now, as one article on this topic put it, if correlation doesn't mean causation, then what does? So we'll get to that in a second. But here's the idea. Here are all of the ways two variables can become correlated. Now you can have intermediate variables. You could have, z controlling x through a, for example. But basically, this is it. This is every possible way. And so when you think that you have a cause, one of the first diagnostic questions you can ask yourself is, which case am I in? Right? So, for example, we see that countries which have more guns have more deaths by firearms. I think many people come to this interpretation first. Having gun causes deaths. But this is also a consistent interpretation, and so is this. And so if we want to claim that guns cause firearm deaths, we have to rule out these cases as well. And that's where things start to get difficult, because often these cases are very hard to rule out. Now this case, the correlation is due to chance. We are going to study that extensively in the next class. The next class is going to be all about statistical significance and randomization. So in this class, we're just going to talk about these other cases. In particular, the case of the confounding variable, which is that triangle form. This is one of my favorite charts from the sadly departed OkCupid blog. It was called OK Trends, and it was data analysis on OkCupid dating.
What happened to the blog?
They shut it down when OkCupid got acquired. I think it was last posted in like 2014 or something. I know why, right? It's so interesting. So this was an analysis of response rates, women responding to a first message from a man, and the average response rate was like 30-something%. It was a different time, and saw that messages containing certain words had particularly higher than normal or particularly lower than normal response rates. So, what's going on here? Why do we see this data, this pattern of data? Yeah, don't be creepy, right? So, right. However, this data was introduced to me by a data scientist who was giving a talk on causation. And she said, yeah, okay, but there's an obvious confounder here. So by that I mean, what is a factor, some unknown factor, that causes both a change in response rate and this particular type of language to be used?
Creepiness.
No, because the creepiness is not observable, can only act through language, because all you have is the language.
Okay.
I don't understand your question. What was the factor that...
So what I'm saying is maybe it's not true that the language causes the response rate. Maybe something causes both the language and the response rate.
Is it like a generic template message?
Interesting, but no.
Personality.
Yeah, okay, so it could be some other aspect of the language. But I'm actually looking for something a little different, which is this. So if someone has a hot photo up, they're more likely to get comments on their appearance, and they're more likely to respond at a lower rate because they get more message. That was the argument. Now, I don't know in reality the ratio between these two effects, and actually I've had people in class come up with like several other confounders. So I'm not willing to look at this data and tell you for sure there's no causal effect between using comments on our appearance and having a lower response rate. But we could say that it's some combination of these types of factors. And the reason I show you this particular example is because the cultural narrative around what's happening here is so strong and so obvious, it makes it hard to even think of confounders, right? So that's the challenge, is when you have a strong correlation to be able to step back and think, what causes this that I'm not seeing? This language of causal models is actually a whole system for talking about the relationships between variables. Generally, the language is, pink means an observed variable and gray means an unobserved variable. And when you're really getting into these social science questions that we get into in data journalism, you're going to want to draw out these types of maps just to orient yourself. How do these variables relate? And in fact, there is a formal calculus of this stuff. You can actually talk about all of this in terms of distributions and variables. You can do this. You can do rigorous statistics on this. There's inference algorithms that try to take a bunch of observed data sets and draw the graph for you. So it's actually not quite true that you can't figure out cause from the data. You can try to infer it statistically. But for our purposes in journalism, mostly it's just a thinking tool. I want you to think through the causal structures of what you're talking about. And finally, I said I would define an experiment formally, and this is tied up in the formal definition of a cause. So talking about relationships between distributions, there's no cause there, right? The cause comes from the idea of an intervention. And so the idea here is that x3 causes x5 if, when I do something to x3, it forces the value of x5 to change. So in the formalism, this is actually called the do operator. And the do operator is what defines cause. So for centuries, people have been trying to talk about cause in terms of correlations and relations between distributions. It's not sufficient. To talk about causes, you actually have to talk about how changing one thing changes something else. And that's what an experiment is. An experiment is changing a variable and seeing if another variable changes. That's how you can tell if you have an experiment or observational data. There's a bunch of reasons we use this intervention definition, but one of the nice properties of this definition is that when we talk about causes, often the reason we care about causes is because we want to intervene to change. If we think that poor childhood nutrition causes poor academic performance in high school years later, we want to find out if that's true because we want to know if we should work on childhood nutrition. Right? That's the point of doing that analysis. That's the point of writing the story, is the accountability. We can see that when these kids aren't provided with lunches, they do worse for the next 10 years. So it fits this idea of an intervention. Not only resolves the statistical problem of what's the difference between correlation and cause, but gives us the answer to exactly the question we want to know, which is, if I change this, will it change something else? Because normally we want to know about cause because we want to control something. So just as an example of this, this is a very nice little experiment that Facebook did a few years ago, and they were trying to figure out if how much people reshared something after they saw it. In other words, if I put something in front of you on the newsfeed, are you going to share it? And there's this whole complicated system of causes that is not observable. So, for example, if someone emails me a link, what the marketers like to call dark social, I may post that on Facebook. The marketers basically just want everything to be Twitter, which is why they work so much with Twitter data, right? So there's lots and lots of reasons why I might go visit it, why I might post a link. And we don't get to observe this, but what we can do if we're Facebook is randomly not show someone a certain link. So that's what they did. For each link, they said, well, normally our algorithm would say 100,000 people see this link, but I'm going to remove it from half of them. And I'm going to see if those people share that link less. And it's a way to decouple the effect of this from the effect of all this stuff. So what this picture, although it's not drawn in the usual way, this is a causal network, a causal diagram. You can see it's split into observable and unobservable variables. And again, drawing this out helps you think about what's actually going on here in the relationship between variables. All right, thoughts on that?
Sounds like a lawsuit.
Oh, because they were experimenting with things?
Well, they're experimenting, yeah. They're on purpose hiding news stories from certain people.
But they do that every day when they tweak their algorithm. I mean, not to dismiss the ethics of what they're doing, but I'm not. So the thing that makes the ethics potentially different is they're publishing research here, but every social media company is changing what you see every day. That's their job. And it's not, I mean, a human editor is doing the same thing, right? Again, it's not that there aren't ethical issues here, it's just that this is a normal part of the job.
There was a story a while back where they were serving up, they were classifying emotional content in these articles, and then seeing how behavior altered depending on if I'm happy or...
The emotional contagion study, yeah. So that was several years after this, and that was the one which became the big scandal and ignited this whole discussion about, is it ethical for tech companies to experiment on us? And geez, I don't know. That is a complicated discussion.
As far as like verifying your correlations, I guess, how do you verify your confounders? Like, this is the right confounder, or like how?
Well, so before you can know that something is a confounding variable, you have to think of it. So the first thing is, from your reporting and from your imagination and your domain knowledge, you have to go through, figure out a list of everything that could be a confounder. And then if you can measure that variable, then you can check for confounding directly, because you can look at the three-way correlations. And there's other methods to talk about cause. You can always interview experts, right? Anything interesting, somebody's going to be spending their whole life on it, right? So they'll know. But you have to imagine it first. And that's often the hard part. It's very tempting to just say, I found this difference.